Hello, this is online class 7. We're going to be covering section 5.3 entitled The Binomial Probability Distributions. It's Friday, October 5th, 2012 for Math 125, and of course my name is Carl Perez. Alright, what I want to start with again, I like to motivate things, get things rolling with a simple example. And we've actually answered this question before in this class. I want us to find the probability of 2 girls in 3 births. Oh, we had questions. We did this in class a few times and had questions on the first exam similar to this. Alright, so I'm going to shorthand it like this. The probability of 2 girls in 3 births. And, well, we know how to do that. We know that in 3 births, there's how many outcomes? There's 8 outcomes. We can list them all in brute force fashion. Boy, boy, boy. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. And on down the line. Alright, so we already know regarding gender, allowing any child to be of any gender in any order. If you're going to have 3 births, you've got 8 outcomes. 2 to the 3rd power, which is 2 times 2 times 2, and that's 8. And we already know if you're looking for 2 girls, well, that means 2 girls and 1 boy, and there's 3 available slots for that 1 boy. So we've got 3 possible outcomes corresponding to 2 girls over 8 possible outcomes, and we get a final answer of 0.375. Alright, nothing new there. What if I was to ask you this question? Find the probability of 20 girls in 30 births. Alright, well, we can't use this very primitive technique here of just listing the sample space and hunting and pecking for outcomes that we desire. It's a little more complicated than that. When we've got 30 births, well, that means there's 2 to the 30th power possible outcomes, and this is huge in billions, maybe even trillions of possible outcomes. Alright, there is actually a formula that will grind this out for us. Let me write that down. We need a formula. Something a little more mathematically significant. We need a formula to compute. And in general, we'll talk about the probability of X successes in N trials. Alright, so this is our goal today, to develop and get some practice using what we call a binomial probability formula. Alright, so what I'd like to do is develop this formula today and get some practice using it for you. But we're going to have to do some preliminary stuff first. Let me write down some preliminaries. First, we've got to write down some necessary conditions to develop this formula and also talk about some new notation. Remember, this is the target, to compute the probability of X successes in N trials. So, for example, 20 girls in 30 births. Alright. Let's talk about what a binomial probability distribution is. Well, if you've got 4 conditions that I'm going to list here, you have a binomial probability distribution or experiment. let's see, a binomial probability distribution results from the following four conditions. Number one, you've got a fixed number of trials. Like in the above motivating example, we had 30 births we were concerned with. All right? Number two, the trials must all be independent of each other. In other words, the outcome of a particular trial doesn't affect the probability of another outcome of another trial. 3. There's 2 outcomes per trial. And we somewhat arbitrarily label these success and failure. And the bi and binomial distribution comes from this 2 outcomes per trial. And the fourth condition you need for a binomial experiment or binomial probability distribution is that the probability of success and of course then failure is constant for all trials. Alright, so if you satisfy these four conditions in your probability experiment, then you've got a binomial experiment or a binomial probability distribution. And you can see where if we're talking about 20 girls in 30 births, well, 30 births, we've got 30 trials. We often say boys and girls are equally likely in any trial, so we can assume independence of births, gender in all those trials. You've got 2 outcomes per trial, typically boy and girl in the above motivating example, and the probability of success is constant for all trials. And again, that's implied with the assumption that boys, girls equally likely in any trial. Alright? Alright, so again, if you satisfy these four conditions, you got what we call a binomial probability distribution. And again, the bi and binomial comes from these 2 outcomes per trial, success or failure. Alright, we've got to talk about some notation to develop this formula. This formula to find probability of number of successes, desired successes in number of trials. Alright, little p equals the probability of success in any trial. Well, if you're talking about 30 births and you're calling a girl a success, then the probability of a success in that experiment would be 0.5, of course, again assuming boys, girls are equally likely in any trial. 1 minus p, I call the complement of p. I'm going to label that q, and of course, because there's only 2 outcomes per trial, this must be the probability of failure in any one trial. Okay. Little n is going to be our number of trials. If you're worried about 20 girls and 30 births, well, then you're talking about 30 trials, 30 births that you're wondering what is the gender of, boy or girl, right? X is going to be the desired number of successes. And again, that label of success is somewhat arbitrary in n trials. And p of x, written in this function type fashion, is the probability of x successes in n trials. Alright, so that's where we're headed. Alright, let me give you the binomial probability formula now. The binomial probability formula. Hope I can squeeze it all on one screen here. It is. Hang on a minute. Let me pause. Alright. Oh, hang on a minute. I'm going to write it in this fashion, a little bit different than the book writes it. I'm going to write it as n choose x, more about that later, I know we haven't seen that operator yet, times p to the x power times q to the n minus x power. Alright, now don't run away. This is my binomial probability formula. It'll give me the probability of x successes in n trials. Alright, well, if little p is the probability of success, then p to the x power accounts for x successes. If little q is the probability of failure, then this term, this factor, represents the probability of n minus x failures, and this is really the number of ways to arrange x successes and n minus x failures. Alright, I'm going to talk more about this in the face-to-face class. Let me write that down. Talk more about this in the face-to-face class Wednesday. It's Wednesday, October 10th. Yes, October 10th, right? October 10th. Alright, and talk a little bit more about how we develop this. Just let me briefly state that this is the probability of x successes and n minus x failures in a particular order. So it doesn't count for all possible orderings of boys and girls, boy, 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 girl, boy, girl, etc. And this factor, n choose x, I call it n choose x, some people call it n combine x, it's the number of ways to arrange x successes and, scroll up a little bit here, n minus x failures. But again, don't panic. We'll talk more about this development of this weighty formula on Wednesday, but I want us to rest in the fact that our calculator has got this function programmed in memory. So in other words, if we take our calculator and call up the right operator, we can enter in a number of trials, probability of success in any trial, number of desired successes among those trials, and we can grind out a probability according to this formula. Okay? Alright. Alright, let me write down that formula again because I'm going to show you how to find it on the calculator. N choose x times p to the x times q to the n minus x. These are products here, implied products, so I'll make them explicit. This is the binomial probability formula. Okay? Our calculator, our TI 83 or 84 plus, our calculator has this formula programmed in permanent memory. And I'll show you how to get there in a minute. How the calculator has it stored, the syntax is binom PDF. Binom, of course, for binomial, PDF for what they call a probability density function. Again, don't panic. The syntax is this. Basically, to run this formula on your calculator, you got to enter in three things. You got to enter in a number of trials, you got to enter in the probability of success in any one trial, and you got to enter in X, the number of successes you're looking for. Alright, let me show you how to get there on the keyboard. Let me get my calculator out to make sure I communicate this correctly. Let's see. You hit, let me write down these commands here. To find this function on calculator, we'll do this. Hit your second button, and then the distribution command. Distr, D-I-S-T-R. It's above, at the second level, above the vars button. So I'll hit second, then distribution, or distr I sometimes call it. Alright, you'll see a sub-menu, and we'll need to scroll down to highlight the binom PDF. You'll see it at address 0 on your list. It's about 10 operators down. Scroll down to the 0 line, 10 lines down, and you'll see it, binom PDF with an open parentheses. Alright, what you'll need to do is highlight this, or highlight the 0 in the list, hit enter, and it'll call this binom PDF command into your calculator home screen. Alright, so this is what you should see in your home screen, binom PDF, just like that, with an open parentheses on the left, waiting for you to input your proper N, P, and X values. Remember, this is the syntax. If you're in a binomial experiment, you want to plug in N and P and X in that order. Alright? Let's use this to find the probability of 2 girls in 3 births. Well, we're doing that again. Well, you know the answer is 0.375, but again, this is practice using this command on your calculator. Alright, so call up the binom PDF operator in your home screen. Now, if you were studying 3 births, your number of trials is going to be 3. There's 2 outcomes per trial, boy or girl, and the probability of a boy or a girl is 0.5. Again, assuming boys, girls are equally likely. And then the probability, we're looking for the probability of 2 successes. We're going to claim being a girl is a success in a birth, and we'll enter in 2, close the parentheses, and hit enter. Let me go ahead and do this here. 3, comma, 0.5, comma, 2, close the parentheses, and I get 0.375. Just like we expected, just like when we grounded out from first principles with a hard list of all the possible outcomes. Oh, notice the comma. I didn't mention that. The commas we put in is above the 7 button. Yes, there is a comma button. Comma button is above the 7 button on your calculator keyboard. It's not at the second level, but it is the button directly above the 7 button on your keyboard. Okay? Alright, well, so we can do lots of things now. We can, using this binom PDF operator, again that stands for probability density function, we can generate the number or the probability, number of successes in n trials for values really limited only by the memory of the calculator itself. Alright, to run this command, or a little more information about this command, there is a using technology box in your text. Let me write that down. See the using technology. We've talked about this before in the course. Gray box on page 224. And of course, we're going to restrict ourselves to the TI 83 or 84 plus entry in that using technology box. Again, this is for further info on this command. And please refer to that using technology gray box on page 244. Alright, what I'd like to do now is use this command in some examples, some homework type examples in our text. So let me get a fresh screen here. And I'll tell you what, before we do that, let me cite the example so you can read it and get familiar with it before I work out the example. See exercise 18 on page 226. Right. Please pause the computer screen at this time and turn there, read the problem, get familiar with the problem, then I'll work it out on the next screen. Please pause now. Alright, here we are with number 18 on page 226. It says in exercises 15 through 20, assume that a procedure yields a binomial distribution with a trial repeated n times. Use table A1. All right, whenever the book says use table A1, we're not going to use table A1. All right? We're going to use our very powerful binom PDF command, right, that we just showed you how to use in a simple example. Alright, use the binomial PDF command to find the probability of X successes given the probability of P success on a given trial. Alright, so if I look at 18, 18 cites an n equals 14, desired number of successes is 4, and let's assume a probability of success in any one of those 14 trials is 0.6. Alright, so I can plug this out. The probability of 4 successes in 14 trials is equal to what? Well, we know it's equal to binom PDF, where your number of successes is 14. I'm sorry, the number of trials is 14. The number of successes is 4. I messed it up. Hang on a minute. Let me write that down again. You know what? I'm going to redo that. Hang on a minute. Well, we want binom PDF, and it's easy to mix up the syntax. The number of trials goes first. The probability of success in any one trial goes next, and then the desired number of successes goes next. All right, so let me grind that out again. The binom PDF. All right, so here we've got 14 trials. What's the probability of success in any one trial? Well, we are told by the author it's 0.6. And what's the desired number of successes? You got 4 successes you need. So let me go ahead and plug this into my calculator. sure I'm doing it right. Again, I hit second, distribution, scroll down to the 0 entry, call up the command into my home screen. I got 14 trials, comma, 0.6 for the probability of success in any trial, comma, and then we're looking for a particular 4 successes in 14 trials. I grind this out, and I get 0.0136. It's pretty easy, please. And I suppose our author would call this 0.014, following their tendency to round off probabilities to 3 decimal places. So again, in 14 trials, you'd be here all day writing all the possible outcomes with 2 outcomes per trial. But here, quite literally at the punch of a few buttons, we get this answer very easily. Okay? Alright, let me ask a question. You might see something like this on test example. And this is my own home-brewed example. I'll say find the probability of 25 girls in 50 births. Can you imagine writing out the sample space for 50 possible births? You'd have to have a string of 50 boys, boy, girl. You'd have 2 to the 50th power possible outcomes. Just way, way too many to list in the brute force fashion in which we did the motivating example at the beginning of the period. Well, with the calculator now, this is a breeze. So let me write that down. The probability of 25 girls in 50 births. Well, let me tell you what not to do first. So a lot of students will make this mistake. Hopefully this won't happen to you. They'll say, well, you got 25 girls over 50 births, so the probability is a half. Now, this is really wrong. This is usually wrong. So please don't let this happen to you. It's a lot more sophisticated example than that. Well, if you're looking for the probability of a certain number of successes in a certain number of trials, and you've only got 2 outcomes per trial, you've got a binomial experiment, or a binomial probability distribution. So I can use my binomial PDF operator. Again, PDF stands for probability density function. NPX, right? N, comma, P, comma, X. So we don't mess up the order again. This is going to be binom PDF. We've got 50 trials, 50 births in this experiment. Again, if we're assuming boy and girl are equally likely, we're looking for 25 girls, so we're calling girl a success. Right? So, and because boys and girls are equally likely, we'll set that P at 0.5, and you're looking for 25 successes here. All right, let me grind this out with my calculator. Again, I'll go to second, your second button, then the distr for distribution command, and you can either scroll down to 0 or you could just hit 0 and it will call up that binom PDF command in your home screen. Let me write that down, or just press 0 to get that for particular function address, that particular operator address. Alright, I'm going to enter in these values here. 50, comma, 0.5, comma, 25. Close the parentheses, and I get a probability of 0.112, I'll call it, for the probability, when we lost sight of 50 girls, let me write that down again, probability of 25 girls in 50 births in this simple binomial experiment. Okay? Alright, so we've done 2 or 3 examples of how to use the binom PDF command, and I don't think it's too tough. Hopefully you're catching on pretty well. Now, a lot of these homework problems talk about an at least and at most scenarios. So I want to take a few minutes to talk about that before we call it a day, because you're going to run into it. What happened here? You're going to run into it on the online exam, and of course the face-to-face exam also. So, at least, at most, concerns. And let me show you what we're talking about here. I picked the simplest example I could, the homework exercises, to introduce this. This is number 33. Number 33 on page 227. It's in the homework list. Alright, so please pause at this time and familiarize yourself with this example, and then we'll talk about it when you get back. Okay? Please pause now. Alright, I'm going to read the problem here now. Maybe we should read it together. Number 33, genetics. 10 P's are generated from parents having the green/yellow pair of genes, so that there is a 0.75 probability that an individual P will have a green pod. Alright? Find the probability that among the 10 offspring P's, at least 9 have green pods. Alright, at least 9. Well, here we haven't encountered that situation yet. So we've got a binomial probability distribution because we've got a fixed number of trials. We're looking at 10 P pods. Right? And we're looking for a certain number of green P pods, so we're going to call being a green P pod a success here. The probability of a green P pod in any P is 0.75. The author tells us that explicitly. So I want the probability, not that X is 9. The book says X is at least 9. So be wary of that at least and coming up at most situation. X has got to be at least 9. Well, that means 9 or 10, right? If X is greater than or equal to 9, that means X equals 9 or 10. Let me write that down in a little informal fashion. We want the probability of at least 9 green pods in 10. Well, I can put that in statistics symbols. I say that's equivalent to the number of successes, and remember X is your number of successes, being greater than or equal to 9. Well, I can say then that's the probability that X is 9 or X is 10, right? Alright, again, when you're connecting things with an OR statement, remember the addition rule claims we can add these individual probabilities together equivalently. So I can say this is the probability that X is 9 plus the probability that X is 10. So all I have to do here really is use my binom PDF command twice to grind out these two values of probability for each of these cases. Essentially, I have to add up the 9 case and the 10 case. So if I go to my TI-83 calculator, you're going to have to punch in some information here. You've got 10 trials. The probability of success in any one trial is 0.75. And first I'm going to look for the 9 case, and then I'm going to add to that the same operator evaluated at the 10 case, right? See if I can get all on screen here. Alright, if I punch this out on my calculator, this first term turns into a 0.188, and then I punch it in again using the 10 case, and I get 0.056. Now, it's a lot of button pushing, but certainly a lot easier than listing a sample space with all possible outcomes for 10 trials. You'd be here all day. Alright, all I got to do now is I use the power of the calculator to easily give me each individual case here, add these two probabilities up, and that's my final answer. Right? So it's kind of lost in the upper reaches of the screen here. So let me label that answer again. This is the probability of at least 9 green pods in 10 pods. And so we essentially add up the 9 and 10 case together with our binom PDF command. Alright. The author then asks us, is this unusual? Alright, let me talk about that. His exact words are, is it unusual to get at least 9 peas with green pods? Let me read that again. Is it unusual to get at least 9 peas with green pods when 10 offspring peas are generated? Why or why not? The book embraces this guideline. And they really could be a bit clearer about this in the text. An event is unusual if its probability is less than 0.05. And now this may seem, again, somewhat arbitrary. 0.05 represents a 1 in 20 chance, right? 0.05 is 5 over 100 or 1 over 20 equivalently in a simplified fraction. Alright, so if your probability of any event is less than a 1 in 20 chance, we call this unusual. Alright? So if we embrace this guideline, this event, 9 green, oh, let me erase that. Technically, it's at least 9 green. At least 9 green peas in 10 is not unusual according to this guideline. Why? Because the probability is not less than 1 in 20 or not less than 0.05. Okay? So when you see problems in the homework list, we're talking about unusualness. This is the guideline the author is somewhat wimpily pointing to. Alright, I want to do more examples like this. Let's see. I think I've got one more. Or is it 2 more? I think I got one more here. Let's look at number 37. Another exercise from the homework list. This is number 37 on page number 37 on page 227. So please pause the screen and turn there now and get familiar with the problem statement. Please pause now. Alright, I'm going to I'm going to read the problem out loud over the internet here, and then I'm going to do the ABCD parts. Alright, number 37 talks about Nielsen rating. The television show NBC Sunday Night Football broadcast a game between the Colts and the Patriots and received a share of 22, meaning that among the TV sets in use, 22% were tuned to that game, based on data, etc., etc. An advertiser wants to obtain a second opinion by conducting its own survey, and a pilot survey begins with 20 households having TV sets in use at the time of that same NBC Sunday Night Football broadcast. All right, right away, I know I'm going to have 20 trials here in all these sub-problems A, B, and C. All right, so let me write some of this stuff down. Let's look at part A. Find the probability that none of the households are tuned to NBC Sunday Night Football. I'll just abbreviate this. What's the probability that none are watching this NBC broadcast? Well, that's the probability of none are watching NBC football. That's going to be probability of 0 successes in how many trials? Well, again, the survey involves 20 households. We're asking 20 people, did you watch NBC Sunday Night Football? And they respond yes or no, and we're looking for the probability of that none of them were watching. Alright, so this is a binomial experiment, 2 outcomes per trial. The assumption is all these trials are independent. So let me write down the number of households we're surveying here is 20. The probability of watching NBC football. So we're going to call watching NBC football a success, and we're told that happens with a 22% or 0.22 probability. And x here is going to be 0. Right? So I can grind this out very easily now with the power of my beautiful calculator. Binom PDF. You've got 20 trials. The probability of success in any one trial is 0.22, and you're looking for 0 successes. Alright, if I grind this out on my calculator, let me get my calculator out. And again, I'll make sure I'm doing it right here. Second dister 0 to get the command on my home screen. 20, comma, 0.22, comma, 0. And I get a decimal value of 0.00695. I'll call it 695. I think the author lists this answer as 0.00695. So, and that is very simply the answer to part A. Right? A simple and straightforward application of this binom PDF operator. All right, let's look at part B. Part B says, find the probability that at least one household is tuned to NBC Sunday Night Football. All right. I'll just abbreviate the event of watching NBC with the initials NBC. Alright, well, that's really the probability of at least one watcher in 20 trials. Hope I'm not over-explaining this. Whoop, what happened? Hang on a minute. Alright. So I hope we can agree that at least one means, well, you're looking for number of successes being greater than or equal to 1 in terms of the binomial probability distribution. Alright, now I know what you're thinking. This is going to take too long. You're going to have to grind out the 1 case, plus the 2 case, plus the 3 case, and go all the way up to 20. You're going to have to work this formula out 20 times. Well, there's a nice little shortcut here. I think we can all agree that if we add up all the possible values of x can be 0, 1, 2, 3, 4, all the way up to 20. The sums of all those probabilities will be 1, because this is, after all, a probability distribution. I claim that the probability that x is greater than or equal to 1 is simply 1 take away the 0 case. Right? If x is greater than or equal to 1, that includes all possibilities of x except for the 0 case. So, and this piece right here is the answer to part A, is it not? So all I really need to do is take 1 minus, the answer to part A was 0.00695, and if I punch that out on my calculator, I think our author calls this 0.993. So learn to think about these shortcuts when you're talking about at least or at most type scenarios here with the binomial probability distribution. Alright, I'm going to do part C and then we'll call it a day. Get a new layer. Alright, part C. Let's just say, find the probability that at most one household is tuned to NBC Sunday Night Football. Let's just see there. Hang on. Let's see. What does that most one mean? Well, that means x is less than or equal to 1. Is it not equivalent to that? So at most means that value or less. And, well, we're going over x values only range between 0 and 20. So if you're talking about being less than or equal to 1, well, that's going to be the 0 case added to the probability of the 1 case, right? Now, again, I can grind these out. Binomial PDF. We're talking about 20 houses here, with 0.22 being probability of success, and we're looking for 0 successes in the 0 case, and of course I'm going to try to squeeze this in here. Let's Binomial PDF. We want to worry about the 1 case here. The probability of 1 success. Alright, well, I know what you're thinking. The binomial PDF, the 0 case, again, that was the answer to part A. So, look for little shortcuts like this. No sense in punching it in again. And the probability of the 1 case, well, if I punch this out, let me do it here to make sure I got it right. Second distribution 0, 20, comma 0.22, comma 1. I get 0.0391. Let me write that down. 0.0391. So, and that's that 1 case. All right, and I think that'll satisfy our question very well. So 0.0461 is our final answer, and that agrees with the book's answer. So this is the probability of at most 1 viewer in the 20 households, viewer of NBC football. Alright, so we've done 4 or 5 rather detailed examples today. We're approaching the 49-minute mark, so I'm going to call it a day. Please work out your homework exercises before attempting the online exam. And again, due to the fall break, as you see in the email, online exam 7 is going to be due the Wednesday morning of our return. Wednesday morning, that's going to be October 10th at 9 a.m., right? 5th, 6th, 7th, 8th, 9th, 10th, all right? And of course, we're going to have a face-to-face class on Wednesday, 10/10. And please bring questions. Some of us, maybe not enough of us, are asking questions on the face-to-face class day. If I don't get questions, I'm going to assume everyone knows how to do every problem perfectly. So please come prepared to bring questions in the face-to-face class, okay? And also questions about homework. Oops. Questions about homework. And questions about the online quizzes, too. For the online exams. All right? Please feel free to print out your online exams and bring them to class. And some of us have been challenging these questions, and that's wonderful. We'll certainly accept all these criticisms in a scholarly environment. So please come prepared to bring questions about, again, either homework or online exams. All right, I'm going to call it a day. This concludes Online Class 7 for Math 125 Fall 2012. That is all.